Assalamu alaikum. This is Dr. Usman Paracha, and today we would have our lecture number 9 of the subject Applied Quantitative Analysis and Practices. Previously, what we had in the last lecture was regarding the methods of calculating measures of variation, how we had to calculate various measures of variation in SPSS, and just for the recap sake, our main measures of variation were related to the range, the variance, standard deviation, and regarding important another factor which is related to the z-score as well. So basically now these measures of variation have got extreme importance in the subject, as we had discussed before, and this is the second phase of examining any kind of investigation in this case regarding the variables which we are trying to view. So we just went through how to calculate these various variation measures in SPSS, and again, like descriptive analysis, these measures can be calculated in SPSS through various ways. We went through nearly all the methods through which these can be calculated. Then we went through how to apply the contingency table concept, which we had discussed before, and how various variables can be recoded in SPSS, because it's very important that sometimes the variables have to be converted into a more meaningful form so that some more interpretation of data can be done effectively. So recording of variable tool in SPSS plays a very important role in this case. Again, we have the option of recording a specific variable into the same variable which exists there, or into a different variable, but then it depends upon the user. Recording the variable into the same variable then would be deleting the previous variable data, which is normally not advisable. So basically we use this tool to create a totally different variable under a different name, so that the original data remains saved, so that it can be used further in other analysis as well. So then afterwards we went through the z-score. Z-score is very important because it's a further interpretation of standard deviation, and normally in latest analysis, instead of mentioning standard deviation, normally the z-score of a variable is highlighted and is interpreted in various analysis. So basically we calculated to just interpret the standard deviation of a specific variable from its respected mean, and in this case then it becomes very easy to identify which values of a specific data set are outliers or not. Specifically when we have got large data sets. So in case of large data set, it's then not that much easy to keep on creating histograms or frequency table and keep on looking on the data minutely in every micro aspect, but instead just generating a list of z-score can easily tell us where the outlier value is lying. Based on that z-score, then we had a discussion about the shape of distribution and how to determine the specific shape of that distribution. In this case, we have got some very important indicators called skewness and kurtosis. So what are the implications of skewness and kurtosis was discussed, and they also shape the various aspects, and again the shape of distribution depends upon the median and mean of that distribution. So once we have determined that, then the shape of that specific distribution will be determined and then quantified. Then after that we went through the various quartile measures which play an important role, and then based on those quartile measures, how to carry out the box plotting. And box plotting is another descriptive measure which is used to carry out the descriptive analysis in order to show where is the spread of the data and how it is equally distributed. Now in this case, that's why sometimes box plotting plays a very important role, sometimes more important role than the histogram. So we just went through that structure, and going to the detail basically regarding box plotting, we went through a 5-number summary, and which basically define the spread of data in box plotting, and again the quartile measures as well. And in this case, first we have the smallest value, then we have got the first quartile, which represent the distance between the smallest value and the first quartile, and this is the 25% of the whole data set. Then comes the median, which is the middle value, also represented by Q2. Then comes the third quartile, which is Q3, and the distance again from the third quartile to the largest value represents the 25% of the whole data set. Now in between this first quartile and third quartile lies the 50% of the whole data, and it's also termed as the interquartile range. Now majority of the data lies in between these two, and the more the data lies in between these two quartiles, the more the normal data would it be. So just going through graphically, here we just have a graphical interpretation. We just went through it before, so just having a recap on it. We are having the smallest value, and then we have got the 25% of data. After that we have got Q1, then we have got again the 25% data and median, and then the 25% of data and Q3. So after Q3 there is 25% of data, and then we have got largest data. So this is the structure of the box plot, and normally this can be displayed horizontally or vertically as well. So here again, this is a situation in which we have very symmetrical data, and in case of symmetrical data we have got equal number of distance in each end, and again as it is shown that we can have this box plot in vertical direction and in horizontal direction as well. So basically this kind of data is shown through a histogram. We have discussed about that, and histogram also gives us some idea of where the outlier is lying, but box plot is a more effective way of doing the same thing. So just having go through how to draw a box plot. Let's go to the software here. Here we take the data set which we have been getting before, and in this data set, as you can see, we have got all the variables of the model which we discussed before in previous exercises. And here you can see we have got 6 training variables regarding TR1, TR2, TR3 and so on to TR6. So if we want to have a box plotting of an individual variable in order to know the nature of the data, so we just go to Analyze button and we click on Descriptive Statistics and we click on Explore, and we just click on the training variable 1 and we include it in the dependent list. So clicking on Statistics, we want to have outliers, so we click on Continue. We want to have some plots, so we want to have an histogram as well. Then we click on Continue and we click on OK. So our results are shown here, and as you can see, among all the other details which we have gone through before, we are shown a box plot at the end. You can see on the screen here that the box plotting is shown, which is a very ideal case here, and in this case you can see the lower side also representing the smallest value here, and here from there to the first quartile, which is being shown in the arrow here. In this case, this is the first quartile here. Then we come to the central black line, which is shown by median, and then here at the top there and with the arrow is shown this I would say third quartile, and then is the last one, the end largest value of x here. So in this case, this is a very ideal case in this case of box plotting. However, we can also have a look of other box plots, and it can also show us some more evident value. So let's consider another data set which is shown here in the screen, and in this case you can say that there are 5 variables defined here, as we can have a look at the variable view option. In this case, the first variable is just a participant code, and after that there's a second field, second variable, which represents the variable termed as revise, which basically indicates the time spent by a certain number of students which they took to revise the material before taking their examination. So the time taken to revise that material is noted here. Then comes the third variable, which is represented by exam here, and which represents the student's exam performance in percentage. Then is another variable termed as anxiety, which is represented by exam anxiety, the anxiety experienced by the student before the exam, and has been measured here through a questionnaire, and the questionnaire was handed over to the students, and then they rated the various questions, and the questions were then measured through a scale, and that scale was then again measured and entered and then finalized in the form of a certain figure. So the last variable here is represented by gender. So coming to the data view here, we can see the various values of the time spent in revising in second column here, and then we have the examination performance of these students in the form of a percentage, and then we have the anxiety score of these students, which has been measured through questionnaire, and we have also enlisted that, and then we have got the gender in the form of male or female. So let's say we just want to find out the box plotting of the variable terms as anxiety here. So we click on Analyze, and by clicking on Descriptive Statistics, we click on Explore, and we can select anxiety here, and then we include it in dependent list, and we just click on OK. So having a look at the results, here you can see is the box plot of this data set, and here you can see below the smallest value there are certain values which are indicated here, certain dots, and in this case these circles have got some numbers written here which represent the case number, which is in fact the row number, and SPSS is indicating that this row number value has been an outlier, an extraordinary small value, and then going ahead there are certain stars which are exceeding a certain limit of outliers, and these are termed as extreme outliers, so that's why they are represented as stars, and thus they also are representing the row number or case number, and we can go to that specific row number by clicking on this button here in the menu bar, below the menu bar. So here it's representing go to case, just click on it, and then it asks for the case number. So let's click on the case number 83, and by clicking on 83 and going to that, it goes to the row number 83, and it's showing the anxiety value, which is 20.21, which is basically one of the extreme outliers. So we can detect the individual values which are outliers here through this function. So going through that value here back in the box plotting, we can have a brief overview of extreme outliers in this case. Now we can get the same result through another tool, which if we go to graph and click on chart builder, so here we just click on OK. Let's say if we click on the word in the bar gallery, which you can see here, there is one option listed among others which is termed as box plot. So we click on box plot, and this is the simple box plotting which is shown here. So by clicking on this and dragging this into the center chart preview area, we have selected this thing. Now let's say we want to have the box plotting of exam anxiety, so we drag it to y-axis here, and we can also have this exam anxiety gender wise in order to know what's the difference. So we drag the gender in x-axis, and then we can click on OK, and we can have some additional results which can shed more light on the analysis we are trying to perform. And here you can see among male the values shown here, and the outliers are shown here in the form of again dots and then star, then we can have a look at the nature of data. You can see that the smallest value in females is higher than the male ones, and then similarly the median, the nature of median among male and female is a bit different. Then the distance between the third quartile and highest value is lower in female data set as compared to a male data set. So you can track the difference between these two box plotting by viewing their smallest value, their interquartile range, and then their largest value as well. And similarly, let's have a look at the box plotting of the exam performance of these students. So we drag exam anxiety back, and we drag exam performance here in y-axis, and by clicking on OK, now we can have a look at the exam performance. So here we can see there are no outliers here, but again the nature of box plotting and the nature of data spread is quite different in between these males and females. You can see this very much evidently here. So once we look through it, we can again have a look upon the rest of the data, and this thing, again clicking on graph, we can go to chart builder as well. So here again we have got another option in which the charts options will be differentiated by different colors. So just dragging this in here, we can just select the exam anxiety, and again through this thing we can differentiate between these two different data sets by different colors. So we just have selected gender, we have dragged it to another screen which is shown here under the head of cluster on X set color. So basically the different data sets would be differentiated by different colors here. So it's just that difference. So by clicking on OK, we can see that both the data sets are now differentiated by different colors here, just for the sake of visual difference. Now the same tool, however, can be used to display the histogram as well, and here we can use the same tool in graph, and by clicking on chart builder we can select histogram, and here you can see the first option here is showing the simple histogram, and the next one is the stacked histogram, which is a bit more advanced form. So just dragging this histogram in the central chart preview area, now we can see the chart preview. So here just dragging the variable here, we drag the exam performance, and here you can see the different histogram. Now unlike the previous function in by clicking on analyze and going through the histogram through descriptive statistics, here you can have different option in histogram. You can define the limits of histogram in this by looking at the element properties dialog box, which is at the right of this chart preview area. Here you can have different statistics in histogram. For example, if I click on this statistics part, you can have the histogram shown as histogram or histogram percent, or you can have the count, or you can show the histogram through any number or any measure you like, which is deemed appropriate to you. So for now we just want histogram here, and we can click on OK. So here we can see the standard histogram, which is shown here. Now if we want to show this frequency as percentage, we can click on graph again. We can select chart builder, and by clicking on histogram percent here, we can click it, but we would have to click on apply button here, and then we can click on OK. So here the same frequency percent is being shown in the form of percentage here, and it can be seen here as well. So this is one of the different form in which the histogram can be displayed. And again, by clicking on a graph and chart builder, we can have additional different options as well by clicking on set parameter, because here in this option we can select customize the number of intervals we would like to have. So by clicking on custom, the number of intervals we want in these different classes can be defined, as we have discussed in previous slides, that the number of intervals can be predefined, though we discussed that the minimum number of classes or intervals should be 5 and above. So you can define the number of intervals here as well, and again the interval widths can be customized here as well. Likewise, you can see the anchor first bin, and here we can identify the custom value for anchor. That means that the first value or the first interval value can be identified, and the first starting value from which the histogram will start can be customized here as well. So these are various options under which you can display the histogram option, and you can display it as well. Likewise, you can also define the bar style, which is evident here. By clicking on the drop down menu, we can have it as a simple bar, or in the form of I-beam, or in the form of whiskers. So normally we use bar style, which is the most demanding part here. So we would just stick to it, and then we can just click on OK. So basically box plotting and other descriptive measures can be used and can be gotten through these various different ways which we have displayed here in this graph, and they are very much effective. In case of graph option, if you want to generate these descriptive analysis in order to get the graph through graph option, you have options to maneuver different details, and you can add or you can customize your preferences here as compared to descriptive analysis option, which you can get through analyze button and going to descriptive statistics. So basically descriptive statistics tool is automated. So SPSS would give you the details by default with certain customized options which have been set by SPSS itself. However, if you generate these graphical analysis through graph option here and through chart builder, then you can customize your preferences here as well. This is one advantage of using graphical aspect in this whole exercise. So coming back to our summary, this 5-number summary which we were discussing, this is the very standard form, and we have just gone through how to generate the box plotting through SPSS. However, the difference basically in the software is that this same diagram is displayed vertically and not horizontally. So rest of the details are the same. The only difference is that the smallest value, as displayed here at the left, is shown at the bottom, and then likewise all the other relevant values like Q1, median, Q3 and largest value are displayed above. So this box plot also then helps us in determining the distribution shape. And in this case you can see that if we have got a larger distance between Q1 and Q2 as compared to Q2 and Q3, then we have got a kind of a distribution shape which can be termed as left skewed. In case of a symmetry or symmetric distribution, these interdistance between Q1, Q2 and Q3 would be kind of equal. So they would be kind of symmetric in this case. So in a symmetric distribution shape, there are equalities involved, and then if we compare this with the rightmost distribution shape, here we can see that the distance between Q1 and Q2 is less than the distance between Q2 and Q3, and thus based on that we can basically judge from here that it's a rightly skewed box plot or rightly skewed distribution shape as well. So this box plot shape has got dual purpose, and it gives us some additional information in this case. So here we are seeing a standard example in which we have got a certain data set which ranges from smallest value, which is 0 here, and the largest value termed as 27. So here you can see that the first quartile Q1 is located at 2, keeping in view the nature of data. Then we have got the median at 3, and the largest value here is 27, whereas Q3 is 5. Now the distance between Q2 and Q3 is a bit larger than Q1 and Q2. Likewise, Q3 and largest value is quite long. So from this plot we can say that the data is rightly skewed. So the distribution shape can be easily identified from the box plotting. That's why these two distributions can complement each other, because from each value we can determine the box plot, or from the distribution shape the box plot, or from the box plot we can derive the distribution shape. So coming to the next thing, we just discovered previously about the z-score, and going through that we knew that we just have to subtract the mean and divide the value, data value, with the standard deviation to compute the z-score. And we know that the value of z-score less than -3 and greater than 3, then in that case that data value will be termed as an outlier. So the largest value, the larger the value of the absolute value of z, then farther is the data from the mean. So the reason for discussing this z-score terminology immediately after box plotting is that z-score again is one tool to detect the extreme outliers, and though we are using box plotting and also to some extent distribution shape as well to detect the outliers, but z-score gives us more solid information regarding these outliers. So how to detect these outliers or z-scores? We may have done this before. Going to this SPSS basically form, we can just click on the data set which you have of the same model we discussed before, and by clicking on Analyze and by going to the descriptive statistics, and by just clicking on descriptives, we just have to select the relative variable, which is, let's say, training variable 1, and by clicking Save Standardized Values as Variables, we can just click on OK, and if we go to the last column, we can see that the z value of tr1 has been generated, and we can just look around and scroll through the list to find out if there is any z value of any value here which is greater than 3 or less than -3. We can then easily find out whether there is an outlier or not. Now from here we can see that there seems to be no outlier or no value greater than or less than 3 or -3. So just having a look at the other data set we just did, and here in this other data set we can see the exam performance and the anxiety. So just let us generate the z-scores of these variables. So going to the descriptive statistics, and by clicking on descriptives here, let's select exam performance and also exam anxiety as well, and by clicking on Save Standardized Values as Variables, we click on OK, and we can see that the z values of both the variables are generated. So in this way we can say that we can generate the z-score of multiple variables as well through the same tool. So just examining through, let's say, through the exam performance, we can see that there is no specific extreme value or outlier. However, by looking at the same column and to the right of this z exam, we can look at the z-score of anxiety, and we can see that in the 78 number row, the z-score of anxiety is reported to be -3.7, which is basically an outlier. So from here we can just scroll down and we can see easily whether any value is greater than 3 or less than -3, and we can determine the outlier here as well. So basically this is one descriptive way of trying to find out any abnormalities in the data set. So going to the same topic which we have been discussing, so z-score calculation is helpful to us in locating the outliers as well. And then coming to the next part, we previously were discussing the descriptive measures for a sample, which basically in social subjects and specifically in business administration, the sample is more commonly used. But for the standard feature for population, basically there are different parameters, and basically here we would term the mean as population mean, as variance as population variance, and then as standard deviation as population standard deviation. However, the notations in this case would be changed. So coming to the population mean, the formula would be kind of same, but you can see here that the notation for population mean would be represented by mu, and then capital N would represent the population size and the formula would be the same. Coming to the variance which we discussed previously, for sample here the variance would be written as population variance, and here you can see that the population variance is being termed as sigma square instead of the other notation which was being used for sample variance. So the rest of the formula would remain same, with the exception that the population size here would be represented by capital N instead of small n here, and likewise the population mean would be represented by population mu here. Then again the standard deviation would be represented by population standard deviation, and in the form of a sigma. Again the same formula, the only difference is between the variance and population standard deviation is we are taking the square root, and in here you can see that the only difference is that the population mean is represented by capital N. The rest of the numerical descriptive measure would be the same. So the difference between the sample statistic and population parameter is very much significant, and here we can see that the mean here is represented by mu. In case of sample statistic it's represented by x bar. Then likewise variance here in case of population is represented by sigma square, and sample variance is represented by s square, and then standard deviation here is represented by sigma, and then again the sample statistic here is represented by capital S. So basically the formulas remain the same, but the notation and again the terminology would be a bit different in both these cases. So then we have got a certain empirical rule, and if this whole distribution is represented by a bell curve, which you can see here, then as per the empirical rule 68% of the data would be lying within one standard deviation around the mean. So here mu here, which is the mean and which is represented by a center line here, and this around this mean the one standard deviation distribution around this mean would be representing 68% of the data. So normally, no matter what kind of data set is, under a normal distribution bell-shaped rule, here the 68% of data will lie in between these two limits. So then again another implication of this empirical rule is that 95% of the data would lie in between two standard deviations around the mean. So as we have already known how to calculate the standard deviation, and by calculating those two standard deviations by multiplying it the standard deviation with 2, we can assume that the two standard deviation in positive side and two standard deviation in negative side would give us two limits within which the 95% of the data would be lying under normal circumstances. Likewise, again 99.7% data would lie in between three standard deviation in terms of positive side and negative side as well, as you can see here in this diagram. So here again you can have a look. Previously here basically the end limits are shown here, and you can easily have a look at these basic end limits here and here, because both these limits are calculated by first calculating the mean, which is represented here. Once we know the mean, then calculating one standard deviation and then multiplying it with 3, this one standard deviation here, or represented by 1 st here, and likewise 2 times and then 3 times of standard deviation would give us this extreme limit of 3 standard deviation. And likewise, if we do it for negative side as well, we can say that these 2 extreme limits would entail basically 99.7% data under normal circumstances. So once we have gone through this empirical rule, we can take an example. For example, there's a variable comprising of standard math score, and it has got a mean of 500 and the standard deviation of 90. So basically, by keeping in view this standard, we can calculate that 68% of these test scores would lie between 410 and 590. So basically, again, this 490, 410 and 590 have been calculated by taking the mean, which is 500, and by first adding the first standard deviation, and then by subtracting this standard deviation from 500, we can identify these 2 limits within first standard deviation, and we can then assume under empirical rule that 68% of the test takers would lie in between these 2 limits. So likewise here you can see that similarly these 95% of the test takers would lie in between 320 and 680. Again, here we have just calculated the values by subtracting 180 from 500, 180 being 2 standard deviations, and we just multiplied 90 with 2, and likewise then we added 500 with 180 as well to find out the other limit. And by getting these 2 limits through adding the standard deviations and subtracting the standard deviation, we can then identify the standard limits within the real data in which 95% of all test takers' scores would be lying. So then in the last part of the empirical rule, we can also identify 99.7% and test takers may be lying between 230 and 770. Again, the calculation has been made by first having the 3 times standard deviation and then adding that and subtracting from the standard mean would give us the limits within which the 99.7% values or scores of test taker would be lying. So this is one effective way to identify the limits within which the data score would be lying under this empirical rule. However, it must be certain that the distribution should be normal. Then coming to another rule, which basically Chebyshev Rule, and in this case this rule states that no matter how the data is distributed, at least this percent of the values will fall within k standard deviation of the mean, and in here k is greater than 1. Now in this case we are given a certain formula which is in the form of 1 minus 1 by k square, and the whole terminology has been multiplied by 100%. Now here you can see that k standard deviation of the mean can be determined, and the examples are given here. In case of k is equal to 2, then we have got 75% values lying in between, and if k is 3, then we have got 88.89% values lying in between the mean data set. So basically empirical rule is more followed in all these cases, and this rule is again another exception which is not much normally considered. So now, as we have discussed between how to generate the descriptive statistics of individual variables, now how to find out the nature of relationship between two numerical variables. Now, in order to do that, basically what we do is have the calculation done numerically first, and then we go through scatter plotting and we plot the values of both variables graphically through scatter plotting, and just to have an assessment of how and what type of relationship that two variables might be having in between each other. In order to know how scatter plots are generated, let's have a look at the data set which we basically had discussed previously. And in this case, let's take the same example in which we were having a data set comprising of exam performance of some students and their anxiety level, and then again we had the variable regarding how much time they spent on revising their exam material. So we can have a scatter plot again through basically graph and clicking on chart builder. Here again you can see under the gallery we have got another option which is termed as scatter/dot. So we click on that, and we have got a number of options, but first we would just have a look at the simple scatter option, which is on which the mouse arrow is pointing. So we click on it and we drag it into center window, and here then let's drag the rest of the variables out. Let's have a look at how and which variables would be examined in order to know the relationship between them. So if we want to know the relationship between the anxiety of the students before exam and their relative performance, so then we drag performance in y-axis and we drag anxiety in x-axis. So let's say we just click OK and we go to the output window, and here we see a pattern which is emerging, and in this case you can see that it seems like both the variables are inversely proportional to each other, because as the value of exam anxiety is increasing, the performance of the students is decreasing, and as the exam anxiety value is low, the exam performance value of those students is high. So based on that, this nature of scattering of data tells us that there is basically an inversely proportional in this case. Now, in order to elaborate this diagram more, we can have a regression line drawn here, and in this case by selecting on the chart we can just in fact even double click it, but even if you don't want to double click it, just right click on the chart and just select edit content and click on in separate window. So here we are being shown a dialog box of properties. Just click on close. Now here, if we want to click, we want to have a regression line drawn, which would give us some approximation of the nature of relationship between the exam and anxiety and exam performance. So we would just click on this basically fit line, which on which you can see the arrow, and by clicking on this button you can see a dialog box which is appearing. I would just drag it on the side. Now in properties you can mention the fit method, whether you want to assess the linear relationship between these two variables, or quadratic relationship, or cubic relationship, or Lewis relationship here. For now we are only interested in the linear relationship, so we select linear and we just click close. So here you can see an approximate line has been drawn, which shows that the relationship between these two variables is inverse. So higher is the exam anxiety score, then the lower is the exam performance. Now from the nature of this data we can see that there are not much outliers involved in this case. So this is the scatter plotting method, which can be used to assess the initial relationship between these two variables. So in today's lecture, basically what we discussed about was the various methods of how to calculate box plotting and how to calculate basically histogram through other tools as well, which is the graphical way by clicking on graph in SPSS menu. Likewise, then we discussed about the various notational changes for population descriptive measures and what's the difference between the sample and population descriptive measures in this regard. Then we discussed the various empirical rules which are based on the normal distribution and how the dataset values would be lying in between different frameworks. And in this case, again, we discussed another extension of the same rule, which is the Chebyshev rule, normally which is not much used, basically. Then we had a look at the scatter plot and how to initially analyze the relationship between two variables and how we can assess the basic linear relationship in between these two by using SPSS. So in this case, in this whole range of topics, we basically applied their concepts in SPSS as well by taking practical examples and how to assess them. I hope that this is understandable to you. Thank you so much. Allah Hafiz.